Okay, before I go over today's class, I want to do something. I just want to show all of you how I'm going to grade your homework assignment number 1. Okay, so here is, let me see. Is this my code or student's code? By the way, I also tell you that if you have problem, you're welcome to just send me the tar file of your code. I have been helping student in this class about their code, what's the bug and things like that, pretty much a few times this week already. I'd be happy to help everybody. Okay, so let me actually, is this the code? Okay, let me just check. Okay. All right, so I want to show you how I'm going to grade your homework. So there are 2 requirements, as I mentioned. The one requirement is that I must have a program which is both client and the server. That requirement, which I'm going to show you, but the other requirement is that I would like to see you actually implement all 4 functions. And each of the virtual function get called at least once. So in this reference implementation, because I only have a 1 function, which is the get distance. And so I'm going to show you how I'm going to see, I mean, regardless how you implement your HW1 client.cpp or the server, no matter how you actually use the real object and shadow object, that's your choice, that's your freedom. But here is what I'm going to do. So I actually will go to the first place I will go to is your virtual function. So I'm going to shadow flight. And typically here, this is the function is called get distance, right? So I'm going to add a code. What I'm going to add a code is here. I will just add it here right before this call. For each of the program, when I actually get it out from you, I would just say c.out, and I would say sfelix boo 1111. That's just my own signature. I will be able to see that. Okay, what I might change this when I really grade it, and then I will say calling get distance. So I just add 1 printf statement in each of the 4 functions because I only have 1 function. So I'm actually only going to do 1 here in the demonstration. Okay, I'm going to add this line to your code when I got it. And then what I'm going to do is I'm going to go to the server part. HW1 server.cpp. And then I'm going to search for get distance. Here's my get distance. And then I'm actually going to add another line here. But this time, I'm actually going to say sfelix1 receiving. Okay, so 1 is calling, 1 is receiving. And then what I'm going to do, I'm also going to make a copy of the same line to HW1, another. Also look for get distance. And also at exactly the same place, I just add this line. Okay, receiving. Okay, so after I add this line, it's very simple for me to, let me just make a clean and make. Okay, so I'm going to. So now you see I have 3 windows. This window, I'm going to do HW1, another. And this window is ./1 server. And then this line is just say ./HW1 client. Okay, so now I'm actually going to look for that. So when I immediately see, okay, there is a line saying that it's calling, so I know this function has been called. right? So I know that, okay, this function has been called. I just need to see one of this in the entire 3 window, just one, then that count as one function, because the same, what I was saying is that you need to make each of the 4 call at least once. And then of course I have to go to server or client to see the receiving. You see, I got one receiving. Now I know that is actually that at least you have a one call that's actually going there, one call that's receiving. I know you have implemented that particular call, at least in the logic flow is actually correct. Okay, that's one thing I'm going to check whether you implement that. But regarding the client server, if you look at the HW1 client, then everything is just calling means that I'm a client. I'm a pure client. And then I go to HW3, another is just receiving. So what does that mean? It's actually only the server without client. But the magic trick is here in the server, in the HW1 server, you see that I have receiving, which means I am the server, but I also is calling, which means that I am the client. So this is the requirement. In fact, that's why I told a few students during the office hour, I said, the code I gave you already fulfilled that requirement because I already have one of the 4 functions is actually doing both receiving and calling. In fact, in your implementation, it doesn't have to be the same function doing both client and server. It could be the receiving is a conflict of interest, and the calling is calling operator equal. That's if you implement that conflict of interest, you actually will see that client server as well, depending on where you put your shadow object. Okay, so that's the way I'm going to check. So I'm not going to check the rest of the message because I know some of you are wondering, oh, how many of the call I need to make. My answer to that, to be honest with you, to fulfill the requirement for you to get full credit, is you do as few, as little as possible, as long as you can actually get the call, such that you know where I put in. I insert this line, printf line, in the shadowfly.cpp. I'm actually also going to add a 2 line in shadow person.cpp, because in shadow person, there will be 2 new functions. One is operator equal, the other one is get VSID. And in shadowfly.cpp, there is a get distance, but they also have a conflict of interest. Okay. Also, I just want to, since I'm on this topic, I want to say a little bit about conflict of interest. So what do I mean by conflict of interest? So conflict of interest, you can actually look at transaction.cpp. It has a conflict of interest, I hope. Yeah, conflict of interest. It's essentially try to compare whether the agent who helped you to book this transaction is the same person is going to enjoy the ticket that they are going to do. So that's why if the TR agent and the flight passenger, they're the same person, then that's a conflict of interest. So it means that it's not necessarily illegal, but just saying that the person who actually booked the flight for this passenger is the same person that's going to board the airplane. Okay, so that's actually conflict of interest. However, the interesting part about this conflict of interest is that in the code, in transaction.cpp is already given to you. It has a equal here. And the equal, because this TR agent is a person and FL passenger is also a person. So this equal is going to trigger the operator overloading, which is operator equal. That's basically the way C++ implement operator overloading, that you can, it looks like it's just a normal code of equal in C or in any programming language, but it has a special semantic we call operator overloading, which it will then trigger when you see that, it's going to trigger person.cpp's, because it's a person, it's going to trigger person's operator equal, equal. Okay, that's how it might trigger this one. So you will be interesting if you have a conflict of interest. It actually might invoke all three functions that you haven't implemented. Because the first is a conflict of interest is going to trigger operator equal, equal. And the inside operator equal, equal is actually going to trigger get VSID. So then you have all three functions potentially. If all of them are shadow function, then they will get called, all of them, and which is then that will fulfill the requirement, just one call. All right. All right. Any question about what I just said about how I'm going to grade this? In case you missed it, we have office hour today. We will also have office hour tomorrow. And I will try to alert my email box. And whenever you send me a code, I try to get back to you as soon as I can. Okay. Any question?
What time is the office hour tomorrow?
Can you speak louder? Sorry, I couldn't
Oh
hear
yeah.
you.
What time is the office hour tomorrow?
4 o'clock.
4
It's always 4 p.m.
Okay. Is there a discussion section happening tomorrow?
What is the discussion hour tomorrow? I actually messed up with this course with the other course. Is this discussion session is 12 or is 4 o'clock?
I think 12 maybe.
Okay. If 12 o'clock tomorrow, I cannot do it anyway. I will ask, see if the TA can help me with the discussion, because I know tomorrow I have a college, our college has a meeting, an important meeting. I'm the representative, I need to attend. So I know tomorrow, I won't be able to do it tomorrow at 12 o'clock, but is office hour, I will definitely be there. Okay.
Is the office hour today, Professor, or tomorrow?
Yes,
today,
both today and tomorrow.
Okay, right. Thank you.
I mean, I usually I don't give like a everyday office hour, but this is a special week. I hope you can get all the help you can get to finish homework 1. So that's why this week I'll try to do as much as I can. Okay. All right. Any other question?
Professor, just to make sure from the announcements, there's no deadline for this assignment anymore, or
there is a deadline for this assignment. But if you make this assignment, I just want to explain, you get 2% extra toward the final grade. You got 2% extra. So after this deadline, yes, after this deadline, there is no deadline, and you can actually just pick up and learning how to do that. And the difference is that, I mean, okay, this is related to the other concept I mentioned. I'm not sure you understand. So typically there is 2 different ways for us to grade, to assign the grade to the student. There's one particular way we call curving. Curving means that we only have a fixed number or fixed percentage of the student that will get a certain grade. For example, maybe you assign 20% of the student to get A. I mean, that's called curving, because you look at the distribution of the student performance. And for me, in my career, I taught college, university since 94. So I've been teaching for 26 years. I've never curved even once. Because when I was a junior faculty, the senior faculty told me the disadvantage of using curving is that it basically introduced the competition among students, and such that they cannot collaborative. They cannot, they kind of has some constraint to enable them completely to help each other to learn. This is called collaborative teaching. There's nothing right or nothing wrong about collaborative teaching versus curving. It's just in the subject I'm teaching, which I think for students to collaborate is probably more important than for me to try to curve. That's why I never curve. So which means that the whatever that extra 2% is just helping those students who actually turn in by the original deadline. They got 2% higher, but it's not going to be affecting the grade for those who actually didn't turn in at this time. I just want to clarify that. And by the way, I can actually show you an example how I actually doing the, what do I mean by not curving? I'll actually just show you one thing. I think this is public. Yeah, it should be public. Let me see. I mean, I remember the last time I used this program. Okay, do I have a, yeah, I have a program here. Let me see. Let me use GF2020. So by the way, I'm a programmer, so I use program to do my everything in my grading. So if you look at my logic, this is actually how I typically grade. So I basically roll the program and I calculate your total points. And I see what's the grade you receive totally, and basically turn that total grade into whatever letter grade you eventually receive. Okay, so you can see that over here, to bump up another student's total by 2% is not going to affect anybody else in terms of their final letter grade they're going to get. Oh, just let you know, I usually give very few A+, 1 or 0. Okay, it's just one particular student, they're so outstanding. They basically, for this case, this student actually get all the bonus from the class, and then just one student got A+, basically. Okay, so let's just tell you that this is how I did the grading, and I hope you understand what do I mean by bump up 2% for those students who can turn in, because they work hard. Just be fair, they work hard already, and they deserve to get a bonus from this process. And for the other student, they're actually catching up some of the background knowledge, which I think is useful for any CS graduate student to learn those concepts. Yeah, does that answer your question?
Yes. Again, just to confirm, we can still submit it after this Friday, but we get a 2% bump up to our grade if we submit it by this Friday, right?
That's correct. That's correct.
Thank you.
That's correct. And yeah, that's good. Okay, so I'm going to continue with the last part of my. I'm actually really anxious trying to finish this this part, so we can actually move on to the second part of the lecture. Okay. Okay, so this part is called VNO. I think VNO is a very important concept. It's just, I mentioned that already. None of the subject I'm going to talk right now, it's going to appear in the midterm. Just to let you, I already say that, so in case you missed it, I hope it's fair to you. You actually know that the midterm has been made already, and then we're going to, oh, the other thing I want to say, I talked to the other student, which I think I'm going to do is the following, that just since everybody here, I talk about how I'm going to do the midterm. So midterm will be during the class. So I'm going to send the midterm in a PowerPoint file or PDF file. I prefer PowerPoint because in PowerPoint, you can actually just modify to fill up the answer. But if in case you don't have a PowerPoint, I can give you a PDF file, and then you actually write down your answer in a separate file using the whatever the standard TXT file or Microsoft Word file. That's up to you. Okay, you can do that as well. But I'm actually going to send the exam to you about say 15 minutes before the beginning of the class. And at the beginning of the class, we will all go into Zoom. And during that time, you can ask me any question for next 1 hour and 20 minutes about any question you have regarding the midterm, regarding whether you have a question or clarification. What do I mean by this? What do I mean by that? So that's the time, about 80 minutes. And after that 80-minute end, you have another 24 hours until the Friday 1:40. So it's going to be from 1:40 p.m. until the next day 1:40. Before that, you have that 24-hour window. You can actually send the midterm back to me, okay, using email. I will actually give more detailed instruction about, by the way, I haven't figured out whether I can use Canvas to do that. So you can actually turn in your document electronically, okay? So one thing I want to say that is the midterm I design, I think is actually, you should be able to finish within that 80 minutes. This is a design. However, some of us have the internet unreliability issue and things like that. So there might be glitches. So I give you a graceful period that you can turn it in, but I don't honestly believe you need that much time to do that. Okay, but anyway, because I think during this very, very unusual moment of time, and both you and me, we're under a lot of unexpected situation here or there. And just for safety, we give you extra time and for you to complete that, okay? Okay, that's what we're going to do the midterm. Any question about what's going to happen in the midterm besides what I just shared? Okay, good. All right, so finally, I'm going to talk about the last part of the first set of lecture is vNode. Is a virtual file system, virtual node. So you can see that we already talk about from device driver, from hardware, hard disk, and go through device driver, we go to the dirty cache. We go to the cache and then we have the FFS, which is a fast file system, which is essentially inode is defined over here. And then we have what we call UFS, which is the Unix file system. This is basically the DRAM, the directory entry is handling. So the UFS is handling directory entry and FFS is handling where is the data block, the pointer block, all this business. And then so far we have been reached until this level. So the next level up is something called vNode. And you can see that that's my object. That once you actually get to the vNode, today we're going to bridge the gap between the vNode, what it is, until all the way to application. What is applications doing all the way so they can connect to the vNode? In fact, file system, it looks like when you're using it, you just use it, just fopen, fclose, you read and write. But in fact, there is so many layers. You can just count on this particular kernel from FreeBSD, how many layers of abstraction you need to introduce. In fact, after you learned about vNode, you will realize that you could actually add in even more layer of abstraction into your file system, and which essentially you provide a, what do I call that? You introduce a flexibility that you can introduce new services. So in fact, a lot of new operating system service that we're talking about today, in fact, is actually going to implement in vNode. Because it's a virtual node, you can think about it's almost like a virtual machine kind of situation, but I'm actually insert a new virtualization layer into the file system so I can actually change the semantics about what you want to do. I mean, just for example, if I want to implement virus scanning, where I'm going to do virus scanning is actually vNode. The way to do FreeBSD virus is in the vNode because I'm adding a virtualization layer for checking whether there is some kind of malicious signature in the file you just open or in the file you just access. Or you can actually implement, say, a crypto file system. So you want to encrypt the content and store in the hard disk. And where do you do the encryption and decryption? Of course, you can do application layer. And the other way to do it is actually, this is basically people have done that initially, is actually implement that in the vNode. So we're going to look at the vNode and up to complete the whole picture. Okay, so first, I'm actually going to show you a structure. You probably already include this. If you're doing Unix system programming, you have a look at sys/proc.h. So sys slash proc.h basically is the data structure to capture all the processes or threads in your operating system kernel. So that's struct proc. So under the process, so this is a little bit, I just want to go over very quickly about a typical modern Linux and FreeBSD system when they have a thread. So you can see that within a single process, they have a multiple, this is called thread. And then they have something called KSC group. So essentially a thread, when they actually map to a hypervisor, is actually going to assign a KSC. KSE stands for kernel schedulable entity. Okay, so that's why you have a thread. A process might have multiple threads, and those threads, some of them are going to map to the hardware or hypervisor. That's why the KSE group. And then that's actually basically included in a file. Okay, so process is a very important kernel data structure to manage all your activity. But that's not what we're going to talk about today, about the thread and kernel scheduler entity KSC. What we're going to talk about is one of the data structure in line 501 is actually called file descriptor. So essentially, file descriptor represents all the file that this particular application have access to. So essentially, you can imagine this is that what is a descriptor? When you want to, this application decide to open a few files, try to access, then you're going to have this file descriptor happening there. Okay, just let you know, this is called P_FD for file descriptor. So essentially, what I'm saying is that you have a process of a table, a process, and which is defined under proc.h. And then over here, you have a pointer to the file descriptor, which is a pointer to the file table entry. So now let's look at what's file descriptor itself. This is under sys/file dsc.h. And you can actually take a look at this. This has a file, and for all the open file, it's actually have a list. So basically, file descriptor is a list of file you just created. And then under the file, now you go to the file. And then inside the file, the things I'm actually going to talk about, there are two data structure. One is in line 115, one is line 118. So there are two important data structure. I'm actually going to show you the second one first, which is the offset. So what is the offset? When you open the file, you actually has a pointer to where the file, which part of the file you're actually interested in accessing right now. So if you have done the system programming, you might use a function called fseek or lseek, S-E-E-K, which allow you to move the pointer from the beginning to a certain location, and when you move that, you're actually setting up the F offset. Okay, so that's one part. Just every file, every active open file has a struct file and then has an offset. Okay, that's number one. But the other thing is very important is that it has a vNode. Okay, now you see that from application process to file descriptor to file. Now you go to the file's vNode structure. Okay, so that's why we have this structure. You have the the file table with the offset. Now you can access to the vNode table. So now we're looking at the vnode. What is a vnode? Let me show you the code, and we will see that how it can be programmed. Okay, by the way, vnode was introduced in late 80 to early 90, at that time by Sun Microsystem. That was a time that object-oriented programming was getting really popular. Okay, by the way, the C++ was introduced in the early 80s. So at that time, everything is defined to be object-oriented. You will see that the vnode, the whole design is also object-oriented. But I want to actually first look at a few data structure, which we already talked about, but we never pinpoint. But now I can talk about is the dirty buffer. So inside the vnode, there are 4 lines code or 5 lines of code. They're actually dealing with a buffer. And you can see that they have, for each of the file, they have some clean buffer and they have some dirty buffer. So essentially, clean buffer is those files you read in, but you never change anything. So for example, you open the file, you access the code, you do something, but you never modify. Whenever you modify, you're actually going to move that buffer to the dirty buffer. So when you move the dirty block buffer, and then you're going to have that list of the dirty buffer. So that's why we're going to do soft update or do journaling, that those blocks are actually matter, because we need to know which part is dirty. We have to do that. Okay. That's the first vnode. So here is the, just want to tell you that this is the, what I call the, usually I cover this when I talk about virtual memory, memory management part of operating system kernel. But I want to just introduce, because vnode is so critical when we talk about the whole idea. So essentially for each of the process, we're going to create a VM map. Okay, it's called virtual memory map, which represent every single virtual memory pieces that you're going to allocate to this particular application. And because the virtual address, for example, 64-bit architecture, the virtual address is 2 to the 64. And we're not going to use 2 to the 64. We only use part of that 64 over there. And essentially, then you will have what we call VM map entry. For example, the first part might be all related to the kernel. The second part is all related to the heap, which you do malloc and free. And the other part, which is probably your stack. And the other part may be some other code you have. So essentially, in your memory management, you have a bunch of VM map entries. So when you access, you actually will need to look at this map, decide where your memory is. Okay. And then they have this shadow object, which is related, in fact, to the homework assignment number 1 you're talking about, but we're talking about. But essentially here you have a VM page, which is inside the memory or the cache memory that related to supporting that map. Okay, and then you have what we call the vnode object. Okay, because each of the map, it represents a lots of memory that within that particular, for example, if this is operating system kernel, then all the pages related to your operating system kernel file is that going to be allocated in this particular range. And therefore, we actually has a vnode to actually represent that. And within that vnode, we have all this VM page. VM page you can think about is a block of memory represent a page or block in the hard disk. And you have, certainly you have what we call dirty pages or the clean page here. Let me show you next picture, you will see that. Okay, I'm not going to show you, talk about this one, VM object, but I want to show you this one. So this is essentially a data structure that's actually try to keep track all the buffer. So in the memory management regarding the blocks in the memory, and usually we have 4 different categories. So we actually have what we call locked one, which is those one are basically A process is basically say, hey, I'm not going to share with other people. I'm going to do something there. And then there is a dirty pages. And then there is a clean pages. You see this arrow going on here and there. It's basically help you to trace the relationship between one page to the other page. And with this data structure, it helps you to actually decide when you actually want to free certain pages or this page is gone, then what pages need to move to the empty table, which pages need to move back from the clean to the dirty. So that is just a data structure to allow you to do that. And in fact, this number, if you look at the number, this number actually represents a order about what is the, by the way, this is the vNode, V is the vNode, and then there is the offset to the within that virtual memory map. Okay. Okay, so that is the list. And so now I'm actually going to talk a little bit more about that's a low level about vNode. I want to just now switch into the vNode as an object-oriented concept. So a vNode, in fact, if you remember this part, the kernel, vNode is not just handling the file. vNode also handle virtual memory, which we already talked a little bit about virtual memory there, and also handle NFS, also handle the network file system, and vNode actually handles socket as well, the network protocol. So if you look at the vNode data structure itself, it actually has a bunch of union data structure called v_un. This handles different kind of file. It handles the socket. It handles the mount. Mount is important, is for both the file system, also for the like a remote file system, such as NFS as well. We will actually talk about that in 1 or 2 slides, but then this will be a topic. We're going to talk to the second set of slides when we talk about distributed system. Okay. All right, so here is the Unix structure for the file system. So a mount is essentially saying that, well, where is your file system? How many partitions that you have? So let me actually show you an example using just my own machine. I have to show my window here. Where's my terminal? If you type a command df, let me make it. If you type a command df, you actually see the last column is called mounted on. So the first part is called file system. So file system represent, you can see that I have a file system represent in this machine, I have a 3 hard disk, or it's actually one single hard disk, but there are 3 partitions. So I have one hard disk, which is a disk 1S1, disk 1S4, and disk 1S3. So basically, that particular hard disk, I have a 3 partition. I have actually formatted to a file system. So when I have 3 different partitions, I want to stitch them together so I will be able to use them together. So you see that this one is the reasonable amount. For example, I mount disk 1S1 to slash. So my slash is actually correspond to that particular disk partition. And then my S4 is actually mounted on slash private var vn. This one is probably my swap space or virtual memory space or something like that. So I mount over there. And then I have a disk 1S3 and mounted I slash volumes recovery. So essentially by doing the 3 mounting, I actually will be able to see all three partitions in a single file hierarchy. Okay, that's the idea of a mount. Mount is a command that you can actually do that. So you can see that I actually, when you do mount, you can see this one on slash, this one on device, and things like that. Okay, so that's what's happening there. Okay, you can actually try your machine. So essentially, what we are seeing in this slide is that I have a 3 file system. That's actually I mount things together. So the first mount may be slash. This is S1, S2, and S3. And they use this mount as a list. So I will be able to, the kernel file system will realize that, okay, you have a mount here, you have a mount here, you have a mount here. So I know how they're mounting together. They have a file system specific information and such that I will be able to see a 3 hard disk or 3 different partition of the hard disk, and they will be logically seen as a one single file system. Okay, by the way, I just want to tell you now I can say a little bit about the difference between symbolic link and hard link. Hard link represent you can actually pointing link within each of the file system, meaning that within each of the mount. So you cannot have a hard link that's actually from one part of the partition pointing to another partition. You cannot do that. Hard link, you cannot cross mount. You cannot cross partition. It has to be on the same file system. Okay, symbolic link, on the other hand, you can actually go anywhere you want because it doesn't have this endless. Also, the other thing I want to tell you is that for each of the mounting point, you have your own inode list. This is a hard disk, so it has its own. This one has its own. Okay, so that's the idea about mount. So let's actually look at what is the most important data structure about the mount is the vnode. So essentially, every file you open, every virtual memory you open or whatever, under this particular file system, it will be stored over here. So essentially, if you have this is actually some of the questions I used to ask students about the difference between vnode and inode. So you have a mount, which you have a local file system with 1 million files. You have 1 million files in this particular mount, but you only open 3 files. Then essentially you should only have a 3 vnode. You see what I'm getting at? It's within this file system, you have a 1 million inode because you have a 1 million file, you have a 1 million inode, but you only open 3 files. So each of the file that you open should have a vnode. So essentially what we're saying is the difference between inode and vnode is inode is persistent. It's always there with or without opening. inode will be there. But vnode is very dynamic. vnode is created when the application wants to access the file, want to do something, then at that time, you're going to create a vnode. And then earlier we say that each of the vnode have a clean page and dirty pages. That's a C and D. So you can see that your file system, this represents your file system in the memory. So from the memory perspective, you have all the mount, you have all the vnode that you can handle, that you're interested, and then with their dirty buffer and the clean buffer. And then so that is basically give you the information you can access to whatever you want. Okay, I want to go, okay, so this is what we are talking about mounting. So essentially, if I have a hard disk partition, remember that we have a boot block, super block, inode block, and also directory block and data block. And then essentially when you want to include the whole file system into a directory, you actually use vnode to do that. So essentially when you, after you link the whole file system, into the vno directory. And when you open a particular file, then basically you have all the vno being open over there. And then they are linking according to the previous slide. Okay, I think right now you already have this. Okay, now this is the figure I was looking for. So this figure basically now try to help you to understand all the way from the top application, from the file table. Then you have a vno. The vno has all the information about that file. And also one thing I just want to tell you, there is an area in the vno, is a pointer to functions for this file. So remember I said vno is object-oriented. So in your homework assignment number 1, for those of you who are unfamiliar with object-oriented programming, that each of the class has what we call member function. And the member function is essentially you want to access the information about this object, you're going to use those member function. So essentially vno is defining a set of member function for you to access this particular file. That's why it's called pointer to the function for this file. And this file actually has a file type. So you might feel a little bit, if you first time heard about the vno, we're actually going to see that a bit later, is that you will say that why do we need the pointer to the functions for the file associated with the file itself as a data structure called vno? Why can't we have the function just a generic set of function that's handle all kind of file? Why do we want to do this way? Okay, that is exactly the trick that the vno, the virtualization is trying to do, is that the function is actually going to be configured differently if you want to have a different type of file. And even more interesting is that you can actually associate different function even for the same type of file. It's almost like a concept in object-oriented programming called polymorphism. So polymorphism means that it's the same class of object, but when you call it, depending on how this object was created, it will be invoking different function to handle the things you want. So it has a really powerful object-oriented programming when you introduce the concept of vno over here, okay? And we will see example that why this is necessary. But the other part of vno is I know information, because you actually from the file table, you got to vno. But then at the end of the day, you still need to access your data. And then basically it's I know information is included over here for you to eventually. So essentially I'm saying that now the vno has the data structure in the middle. It connects to the application. It provides flexibility about what you can do. And it actually allows you to access to lower level, which is the hard disk in this way. By the way, this I know information, it might not be I know. It could be if it's NFS, network file server, network file system. This is actually going to invoke socket to go to the networking and then go to the other machine to pull it out. Okay. Just very quickly recap. This is what we did. What we go over is the file descriptor to file to vno to basically the I know, the D I know and I know. It basically represent one is the D stands for hard disk. So this is the I know on hard disk. This is the I know in memory. Okay, so in fact, you should know by this slide, there's actually also two versions of I know. One is in your memory, one is your hard disk. Okay, so we got to this point. I just want to share with you that there is a piece of code. Very quickly over here, you see that in line 141, there's called V data. This is still in V node. What is a V data? And V data actually provide you to access the lower, the potential lower file system. Okay, so what is a V data? The V data, in fact, is used by the V node with this two macro. Okay, so if your V node represent a local file system, which is meaning that you're going to accessing the file on your hard disk, then that one is actually a pointer to the inode structure in your memory. Remember, this is a structure inode star. So essentially in the program, this is the macro, it's called V2I. How do you actually convert your V node to inode? Essentially, you casting that pointer, that's a generic pointer, void star. By the way, void star is in C or C++ programming. It represents just a generic pointer. So it casting the V node, which is VP is the V node pointer, and casting with the inode. Sorry, it's a VP to the V data, which is a generic pointer. I casting the generic pointer with the structure inode star. So that will, this simple macro will convert your VP, your V node pointer to inode pointer. And similarly, if you look at the same code, in the inode memory version of the inode IP, inode pointer, it also has I underscore V node, which is pointing back. So essentially with this two pointer or this two macro between the memory, in-memory V node and in-memory I node, that you have a one-to-one corresponding if this V node is actually connecting to the hard disk I node. The reason I emphasize this part, I want to tell you that V data, which is the line 141, it could be pointing to something else, depending on what kind of file system, because your underlying might not be I node. For example, if you are connecting to a, say, a FAT file system or a other kind of NTFS, they might not have exactly the same data structure for you to deal with. Okay, but V node essentially, it provides a virtualization layer to cover everything. Okay, so this is the memory I node. Okay, remember there are two functions. Two data structure. I just make sure you don't confuse. There's a one file which is UFSD I node, which is represent the disk I node, and then this I node is actually in the memory part. Okay, all right, sorry, go over here. Okay, I'm actually going to pause a little bit. Is there any question so far about V node? Okay, so now I'm actually going to look at the bigger picture.
Professor, I had a question real quick.
Sure, go ahead.
Could you clarify the difference between the inode on the disk, the D inode, and the inode that's in memory? Is that just the virtualization layer that makes it different?
Okay, the thing is that before you can in fact access a file, you have to access the inode in the hard disk, right? So you have to bring the inode into the memory. You have to first get it into the memory.
Yeah.
When you get to the memory, because now you're actually trying to access the file system, so it needs extra information associated with that. So I actually then create another, I actually essentially map whatever that in hard disk I know into a similar data structure, but with a few other extra attribute associated with that I know. And one of that extra attribute is a pointer to the V node.
Okay.
Yeah, so they're very similar, but there are just a few things.
Just the memory one has a pointer to the V node.
Right. That's a major difference between the memory I know and the other thing which is also important. I think the memory I know also have other pointer related to the buffer. related to the dirty and clean buffer and things like that. They have the pointer. Remember I showed you a picture which they have a pointer from here to there in the dirty buffer, clean buffer. Those pointers are also being maintained in the memory, I know as well.
Okay, thank you.
You're welcome. Okay, so let me just go back to this picture.
Sorry, Professor.
Yeah, go ahead.
Can I also ask a question about vnode?
Uh-huh.
So does vnode also have a vnode block like the inode, or is just in a memory?
No, vnode usually they don't have a block because vnode is, well, of course, a vnode is a will use some block of memory. But when I say block, I usually represent that this block is corresponding to a hard disk block somewhere. So if we talk about this mapping between a block of memory in the memory versus a block of storage in the hard disk, then vnode doesn't have that kind of mapping. It's only inode and the disk block have that. Or virtual memory has that as well, because you're going to do what we call swapping memory, 30 page or page full. You need to do that kind of thing. Then you have that kind of block. But vnode doesn't have it. The vnode is a purely transient data structure that's actually hosting those blocks, but it doesn't have their own block. Yeah. Okay.
Thank you,
so,
Professor.
oh, you're welcome. So now you actually see the data structure to have this vnode here. So far, I only tell you in terms of the data structure, what they are linking related to each other. But now I'm actually really going to go into this layer to talk about what kind of functionality that's actually introduced associated with vnode, that is probably, I think, is the most important concept you should learn in this particular lecture. Okay. It's really powerful for you to do this part. Okay, so this concept is called VFS, virtual file system, and sometimes I call it a file system switch. And what do I mean by the file system switch? You can actually see that. Oh my! For some reason, my PowerPoint. Let me actually do something. Why I have this? Sorry, let's change the font a little bit. Just 1 second. Okay, now I'm happy. Yeah, I don't know what happened that suddenly that particular portion of the slide. Now I feel a lot better with this. Okay, so this is the other view to look at the operating system kernel, but focus purely on file system, and not just focus on one file system. It's actually focus on a lot of different file system. Okay, so you can see that now I have a different kind of file system. I have earlier I said I have a file system called NFS, Network File Server, and I have a UFS, and I have an LFS. LFS stands for Log File System. In fact, this could be any file system. It could be NTFS, could be FAT32, it could be ZFS. It could be any kind of file system that you want to have. And each of the file system, they have their own characteristics about how you want to handle one thing versus the other. So it became, before we have this VFS, it's pretty hard for us to integrate this different file system together. We pretty much have to develop in the kernel specific routine. I have to know that, okay, this is NFS, so I need to do NFS part of the code. This part is a UFS, I have to do UFS part of the code. This part is some other file system, I have to do the other part of the code. So the kernel become not so well structured, which is to add a new file system is typically pretty difficult, because you're going to change a major part of your operating system kernel before you can introduce a new file system. So what they decide is, as I mentioned, is actually incorporate the concept of object-oriented. And essentially what we want to do is we introduce another layer, which is called VFS. So what is object-oriented? Object-oriented, the important thing is providing an object interface, which is the standardized interface to you to access a different type of object that's actually under the inheritance hierarchy. So essentially, VFS is actually providing that. I'm actually providing a virtualization layer such that the upper layer, whatever the system call layer or user space, when they want to access a file, they actually don't need to worry about whether that file is NFS, is actually a local file system or remote file system, pretty much just like what you did for homework assignment number 1. So you don't have to worry about whether it's a shadow or it's a real one. You just call it the same interface. The virtualization layer will figure out how to redirect your request to different parts. So that's why you have this VFS. That's why you have your vNode. So VFS, what is VFS? Is a bunch of vNode and together with a bunch of function pointer, which implement the virtual file system according to what is the layer below that, how I'm going to access to that. For example, earlier I said there is a one variable called vData. If this is a UFS, your vData is going to connect it to the inode. If it's an NFS, it's going to connect you to a socket. If the LFS, is going to connect to something else. Okay, so that is basically the high level structure about the vNode. Okay, so now we're actually going to look at the. I'm going to show you directly the next picture. This picture is more interesting. So this picture is defining all the member function that related to the vNode. So here I'm actually going to show you, of course, you have this generic attribute. You can think about this as regardless your NFS or LFS or whatever, you're actually going to have all this data structure. You have type, you have mode, you have unlinks, you have user ID and file size, access mode file. Pretty much this replicate what you have with inode, but also with other type of file system. We kind of standardize, you have to have that. And then you have a set of generic operator. And the generic operator is essentially say, you want to do with a file, then these are the member function for you to access this file. And this is a standard, by the way. For example, you can look up, this, by the way, this part is directory. So you can actually look up a particular directory entry, and you can actually do whatever, create a symbolic link and or move the file or rename the file, make directory. You can see that this is a function is corresponding to a pretty standard operation that you're going to make a call. Almost every single one I listed here has a system call corresponding to that. So essentially, when you're making a system call, essentially it's a map to calling what we call VOP, is a vNode operation or operator of that function. And what's this? By the way, each of this is a function pointer. Okay, so that's why when you make a system call, you have the standard interface. However, because each of this is a function pointer, depending on whether you're linking to NFS or UFS, then the function pointer for you to support those VOP operator in the next slide is going to be different. So you essentially, by doing that, you allow to, you have a generic interface, which is the purple part on the top, looks exactly the same. But the real function pointer is actually the circle below that interface, the purple interface. And then that one is going to be whatever file system specific. Okay, so that's basically the VFS trying to do. Okay, I'm going to skip this part about get attribute. Get attribute essentially is for you to get the lower part. Okay, that's where we look at just very quickly V node. That's how, remember you say V to I. How do you actually get from the V node to I node? That's actually in the implementation of get attribute that you can do that. Okay, so now I'm going to tell you a interesting situation about NFS, network file system. So we have a client server situation. So this is the NFS server. This is NSF client. So in the client, when you want to open the file, I mean, the user application, they don't know whether this is UFS or NFS. So what is NFS? NFS means that I have a proxy that connect to another server, which have another hard disk, which is the inode. So essentially, if from the user perspective, once you mount using NFS to mount the other server, then you actually don't need to worry about whether it's a local or it's a remote. It's polymorphism, basically. And if you want to access the remote file system, what's going to happen is that it will still, when you open it, it will still trigger this purple interface, which is the vnode standard interface. And that vnode is going to trigger, instead of trigger the inode information, is actually going to trigger the NFS client to actually communicate with NFS server on the other side. So this is pretty much like your HW1 client and HW1 server. So it will be forwarded to the NFS server, and the server is actually realized that, okay, this particular file is actually in my local. It's a real object on my machine. Then it basically transfer that call to another vnode interface, which is SS the UFS. So that's how the NFS works under the vnode scenario. In fact, I almost want to say the idea was vnode was actually developed at the same time NFS was developed. So that's why it's a clear motivation that why you want to use object-oriented to define vnode and such that I can actually include all kinds of new services. And by the way, just for your homework assignment number 1, that it's possible in NFS that this, again, is not going to be UFS. This could be another NFS, and then you are going to trigger another. So it becomes HW1 client, HW1 server, and then HW1 another. Okay, so if you're familiar with this scenario, in fact, you can, using the skill that you learned from homework assignment number 1, you can probably develop a remote file system on the user base, by the way, following very similar philosophy. Okay. Okay, so that's NFS. I think I'm going to skip this part. This basically gives you a step-by-step scenario for you to actually be able to use vnode to actually check the mounting point and try to look at that. I will skip this part to the next part, and then I will come back to here if we have more time. Okay. Okay, I'm going to skip this part, but directly go to this particular part. Okay, so do I have a next slide? Yeah, I do have a next slide. Yeah. Okay, so we talk about this picture. We have user process go to VFS, and the VFS actually go to the lower file system. So what we did is that we can have a VFS, which is encapsulate all the differences in the lower layer. And then we will be able to support both the local file system and NFS immediately. Okay. However, people actually getting really smart. They bring in more idea from object-oriented world and say, okay, if I can provide one layer of virtualization, why not provide more layer of virtualization? If you have a one layer which encapsulate difference, then can I actually introduce more layer so you can have a stackable file system? So the thing is called FIST. So FIST stands for, it's a file system. I think it's called stackable file system, but I don't know why is FI stand for. Okay, sorry. FIST is actually file system, stackable file system, ST. Okay, now I know why the I is a lowercase. Yeah, I forgot about this long time ago. Okay, this is developed a while ago. So FIST is essentially make sure that I can have one layer of vNode to be on top of another layer of vNode. And in fact, from the programming perspective, is you don't even need to modify the kernel. So the way FreeBSD and Linux system work is that when you want to introduce an additional layer of vNode, all you need to do is make a system call to load a module, another layer of VFS module into the kernel. So by the way, the kernel was developed long time ago, was like you have to modify the source code, and then you can change the behavior of a kernel. But since the middle of the 90s and maybe early 2000s, getting more and more popular is what we call loadable module. So it means that if you want to actually change the behavior of the kernel, you can just essentially upload a particular module into the kernel, and the kernel will change their behavior immediately. And one of the module that you can upload is a vNode module. So essentially you upload another layer of VFS. And then of course, remember what's a vNode? vNode is itself is a data structure, but it also has a bunch of pointer to member function. So that module will include a bunch of new functions. So what is a module? A module is a data structure with a set of functions, with the operator like a VOP, whatever you want to do. And then all of this is bundled into a module. You load it into the file system at exactly this location. So I'm going to show you a more specific example. For example, we want to do a antivirus file system. So typically it was a user process to the lower level UFS. But what you can do is you can actually insert dynamically if you have a root privilege and into the kernel. So you actually have a new VFS, and that VFS, you call that layer called antivirus file system. By the way, this one was one of the earlier example when people developed a stackable file system. That why do I need stackable? I want to actually insert. And such that you can see that the read is actually being replaced. It's really just very clever replacing the function pointer that from the lower level read, like an ext2 file system read, and actually change it to AVFS read. So essentially, after we insert this module, that every time you actually try to do some kind of read, you actually go through the AVFS, okay? And when you do the read, you go here, but when the data really come back, it's actually going to do the scan buff. Basically, you're going to do another function that's actually outside of this, either outside of the module or it's even outside of the operating system. In fact, when I did my own implementation of AVFS, I actually put the Oyster and the virtual database in the user space. So essentially what AVS is doing is that is actually whenever the data is coming in, before it's sent back to the user process, it actually first intercepts, send it to my user level antivirus program, and I actually check against my virus database. And if it is okay, I'm actually going to push back to the AVFS, and then AVFS will allow and let it go. Okay, so that is the typical scenario. So essentially, you can actually insert multiple layer of VFS over here, and to provide different kind of functionality, and to help you to dynamically changing the behavior about how your file system is being handled. Okay, I'm actually going to stop here. Any question about what I just said about this picture? This is actually my last slide, and I'm running out of time. Any question? Are you guys still there? Let me check how many students. Oh, you guys are here. Great.
Oh, yeah.
Okay. Yeah, I actually did a lot of implementation with the VFS. Probably none of you took my undergraduate version of operating system. My final project assignment for ECS 150 is ask the student to insert a vnode into the operating system kernel, so they will collaborate with BitTorrent. So essentially, how you can build a better BitTorrent client. That part of that is actually in the kernel for you to be able to coordinate. If I have a time, I will talk about that project, but that's also a stackable file system that's actually allow you to do a lot of programming there as well. Okay. Okay. If you don't have any question, I'm going to close today's recording, and I will have office hour in and out. Okay.